Part 1. Soil is not dirt. Dirt is dead. Soil, however, is jam-packed with microorganisms that make up the foundation of a symbiotic ecosystem. Like humans and other living beings, soil has health. This allows it to continue to sustain vegetation and animals as a living ecosystem. I think this is why we should call the famous dirt and worms cup a soil and worms cup instead. Dirt won't have worms, but soil definitely will. So what are the basic components of soil? Soil is formed by two processes: the weathering of bedrock below and the decomposition of organic matter from the soil surface. These processes lead to the soil's vertical structure, known as the soil profile. Soil overall is composed of an unequal proportion of mineral matter, organic matter, water, and air. Air and water take up the pore spaces, the void in between the soil particles in soil, which ultimately occupies half of the soil volume. The organic matter of soil is composed of undecomposed residues of dead and living organisms or microorganisms. The mineral matter of soil usually consists of 3 fractions of sand, silt, and clay. But soil has more to it than just its physical properties. It has a biogeochemical cycle of its own, the carbon cycle, which plays a huge role in the overarching problem of climate change. So, we have our first guest, the University of Montana's Dr. Justin Gay, who has research interest in soil and biogeochemistry. How exactly does the carbon cycle work within soil?
To make an extremely complex process, hopefully more palatable. I think using the analogy of a bathtub, filling up a bathtub makes sense. So with carbon, the main input is through primary production. So plants, they have carbon, and that carbon is originated from carbon in the atmosphere, and it's assimilated into biomass, and so that is the carbon that goes into the soil. Obviously there's more migratory inputs, from a natural system, thinking about animal excrement or a carcass that's dying and decaying. There's carbon in there that ends up in soil. But in terms of the primary inputs of carbon to soil, it starts with plant matter. And once that plant matter is into the soil complex, there's multiple pathways that it takes before it's either stays in the soil or to released. There's 2 main pools, I would say, and this is kind of coming from pretty old science that we know. There's a long-lasting pool and a shorter-lasting pool, and the words for those are recalcitrant, long-lasting, labile for short-term carbon. And old thinking, we've moved on from this, but old thinking is we thought the amount of carbon that accumulated in soil was related to the recalcitrance of the material going in. So we knew that some plant matter was harder to break down. So plants with high lignin content, which is formed in different parts of plant cells, plants with high lignin would break down slower, and so we thought if we put more plants on the landscape that had more lignin, that we'd build more soil carbon because it was hard for microbes to break it down. We've since realized that that's not necessarily how it works. So when that leaf is in the soil complex and we have microbes breaking it down, those microbes use the carbon from the leaf to respire, just like us. We need to eat things, we respire, we breathe, and that's carbon going out of us. And so I use the analogy of the bathtub, so you're filling up the bathtub with water, that's the carbon from plants going into the bathtub that it will make it increase. But also there's a drain at the bottom of the bathtub, and that's the carbon that's coming out of the soil. And so the first kind of output that we'll talk about is the respiration of microbes. So microbes, as they're breaking down plant matter, they respire, they're releasing CO2 back up into the atmosphere. So that's the first output. And so that's not equal to the carbon that came in, so that's a process that's, I would say, lagged. So you're not losing all that carbon right away. Some of that carbon's going into the biomass of the microbe. And so we know, this is kind of more recent work is showing that a lot of soil carbon is actually dead microbes. So when we think about how to build soil carbon, we need to talk about how do we kind of keep soil microbial necromass. Mm-hmm. Necromass is the word for microbial, dead microbes in the soil. And I kind of going back to the 2 pools, now that we call these 2 pools, like I said, the slow pool and the fast pool. That fast pool we call particulate associated organic matter, you'll see in the literature, or PAOM. And that's you think about chunks of the actual chunks of leaves or chunks of litter, things you can still see kind of like the plant matrix. The other pool that's more resistant to breakdown for microbes is the mineral associated organic matter, so the MAOM pool. And so that pool it's smaller in size, it's stickier, it can stick to clay surfaces and soil, it's a more, it's progressed down the decomposition line further. And so in soil science, when we talk about kind of like building soil carbon, we're really talking about building that longer lasting mineral associated organic matter pool. So kind of like in terms of the big pools that are important for soil carbon, like I mentioned, so the microbial necromass, so we want to get carbon into microbes, we want it to die, and those pools are smaller and can generally absorb to those surfaces of clays. But then also we have the mineral associated from other things, like we know that carbon can be dissolved in liquid form, and so that can like move into the soil, and the dissolved organic carbons can associate with clay minerals and form that mayome pool.
As Dr. Gay goes on to explain, microbes are the main driver of soil carbon. Microbes' respiration are the main output of the carbon cycle. They can control how much carbon is lost as CO2. This is probably why the Earth's soils hold 3 times more carbon than the atmosphere, creating a vital carbon sink in the fight against climate change. He finishes out his bathtub analogy with primary production being the faucet, filling up the tub with carbon. He uses microbes as an analogy for the plug in your bathtub drain, controlling how much water, in this case carbon, drains out. In a rough transition, we began to discuss the effects of global warming caused by climate change. We see temperatures rising all across the seasons, so how does it affect our soil? Does global warming as a result of climate change also, I guess, impede the storage of carbon in the soil? So like is more soil carbon lost because the soil matter like might decay faster?
Exactly, yeah. So yeah, climate change, specifically warming, has a known effect of increasing microbial activity. And so in science we can measure that using a metric called the Q10, or the temperature sensitivity. And we know that like as you increase the temperature of a system, a biological entity, so an organism like a microbe responds exponentially to temperature increases. So for every 10 degrees you increase the activity tenfold. And that is not necessarily great, right? Because we talked about the main loss mechanism of carbon in the soil is respiration. So if we know that temperature causes increased activity of microbes, there's going to be increased carbon loss from respiration. So, and also we just talked about too, we know that in some systems microbes are moisture limited, especially in like these drier, arid, semi-arid systems. So if we're seeing a climate change impact in a region of increased precipitation, there's some feedbacks where you're going to have increased carbon loss, and it's going to be more spotty, right? It's like a rain event. There's going to be infiltration and runoff. So there's going to be a period of time where you see increased activity, but that has measurable impacts on a regional carbon budget.
Okay. Then another question that I sort of thought of, is it like when it gets hotter and say you're tilling in your compost, which like I think it's steaming, right? Yeah, to decompose, and then you till it in, which also increases that, and it's hot. So like, does that sort of increase more soil carbon lossage?
Yeah, like you said, all those practices kind of can compound. And obviously, like all this, should caveat the discussion today is each global region and its particular climate and the soils there act a little bit different. And so we've kind of been talking around mainly like soils in the U.S. and essentially, which are dominated by mollisols, which have this kind of like thick top organic layer of very nutrient-rich, carbon-dense soil. So, but in other regions, the point is like some of these are going to be nuanced in terms of their reactions. But yeah, generally, if you're tilling soil, you're turning it over, you're adding something that's warm, you're going to increase microbial activity that's going to stimulate more decomposition and carbon loss.
Global warming, overall, leads to the decay of soil matter as seen in even the Arctic permafrost, and ultimately more CO2. This becomes a cycle as CO2, lost soil carbon, further warms the earth and causes soil to release more and more carbon. As a segue to part 2 of this podcast, I interviewed Caroline Stevens of the Peace Farm, which is located just 2.5 miles away from UM's campus. Caroline earned her Master of Science in Environmental Studies at the University of Montana, focusing on agriculture, food systems, as well as creative writing. I asked her about how she saw climate change affecting the farm she tends and other farms that she knows of.
In big ways. I mean, I remember when I was in college, climate change, this was back in like 2007 to 2011, climate change was sort of like a theoretical future thing. Even when I was in graduate school and researching climate and drought adaptation, we were writing about it in very future terms, and now it feels very present. You know, I think about the farmers in Vermont who were flooded twice in a year, who were not able to reap a harvest because of this huge flood event. I think of the farmers in Nashville who were dealing with flooding events in Western North Carolina. You know, I think of farmers dealing with wildfire in California. I think of all the farm workers dealing with wildfire smoke and the physical effects that has on farm workers, negative health effects, but also the negative health effects that has for plants. We see plants really slow down when they're not able to access all of the light because it's filtered through smoke. Here on the Peas Farm and in Western Montana, you know, a lot of farmers here lost season extension structures like greenhouse, hoop houses. Those kinds of structures are like a tool to help mitigate some of those like seasonal spring and fall temperature fluctuations. If you have a covered structure, it's like really helpful to avoid some of the losses that can happen when the temps go really low in spring and fall. But those structures were vulnerable to the heavy wind event that we had in July. A lot of people lost plastic, which can be thousands of dollars to replace. And a lot of people, their structures themselves were damaged by wind. And that's very expensive and time consuming to reconstruct those spaces. We also have had just really crazy weather patterns. I mean, it's hard for me to say, are they crazy? Because I've only lived here for a little over 10 years. But just kind of talking with other farmers and other growers and old timers, it's just like, having a July with temperatures above 90, 95 and into the triple digits most days of a month of July in Montana, that's really hot. That's unusual. Having, you know, really erratic, warm, cold, you know, like super freezing in spring and fall, like has happened in the past few years, can be really hard on perennial plants. Perennials are typically thought to be really resilient, but they are also vulnerable to some of these really big fluctuations that don't allow for plants to go into dormancy slowly. Or that can, like if cold temperatures happen during bud break or flowering for perennial plants, that can be really hard on fruit production, for example. So seeing a lot of those events, I see perennial farmers like orchardists struggle. They've always struggled though. And then at the Peas Farm, you know, luckily we have a diversified vegetable model where in any year, there's probably 3 crops that are going to be terrible. And there's probably a host that are going to have done great. And then there's a ton that are going to be average. And that has consistently continued to be true despite some of these crazy weather patterns, because the model that we have is pretty nimble. And because we have diversity built into the system, which is kind of like a built-in insurance policy, some crops are better at adapting to certain conditions than others. And I feel like our model is set up for more resilience.
Do you think you'll have to switch to more like drought and temperature resistant plants in the near future, or even in like the distant future?
The distant future, probably.
Yeah.
Near future, we don't ever make huge changes. You know, we make changes in management in 1 year. It's pretty unusual that we're going to like drop a crop or completely change our varieties, but it's possible. We are lucky that we have a lot of irrigation water and it's very secure. If we were a farmer that didn't have secure irrigation water, those would be other questions that we would have to navigate.
This brings us to part 2, soil to farm. All right. So first question, can I get a rundown of the Peas Farm practices just for like the people who are kind of unaware?
Yes. So for about 25 years, the University of Montana Environmental Studies program has been partnering with Garden City Harvest, which is a nonprofit here in Missoula, to create this place called the Peas Farm. And the farm itself is the primary site for the Peas program, which is a University of Montana program. So major tenets of our soil management include the use of low-till equipment. So minimizing tillage as much as possible and using conservation tillage implements when possible, given that we're growing vegetables and sometimes we need a certain soil quality for seeding things that are very tiny, like carrots, for example. So in order to get that, even farmers who are no-till organic are probably using tillage for even just the top inch or two of soil. We do a little bit more than that. So we have this implement called a spader that has these big shovels that go vertically into the ground and scoop up soil and then kind of propel it onto a piece of metal, and then it kind of crumbles and drops. So this method of tilling preserves the soil horizons, and it also preserves some aggregate structure in the soil. So all of this means that we're losing a little bit less CO2 when we're tilling.
Okay.
That's really important, not only for emissions, but also for the benefit of our soil structure and the ability of our soils to do the work of turning plants into soil carbon or soil organic matter, which is the basis for really good soil health. Having more soil organic matter means your soil holds moisture longer. It also drains moisture more easily. It retains nutrients. Those nutrients are more available to plants. So all these benefits. So we use a spader. It's a conservation tillage implement. It doesn't rototill the soil, which is more damaging to soil structure, and inverts soil horizons and creates a plow pan and all these bad things. So that's one thing we do. Minimize tillage, use conservation tillage tools. Another thing we do is that we use a lot of cover cropping. So this is where we're keeping a living cover on the soil as much as possible. Now, there are places where we're not able to do that because we don't want to build up too much residue in the soil such that we're not able to plant there. But we do a lot of annual cover crops in fields that are being fallowed for a year. We also have a field that's in 3 years of perennial cover crop, which is really like the gold standard in vegetable cropping. So you can do a lot of soil carbon sequestration in those places, and you build a lot of soil organic matter in those places. Now, I will say it's not forever, right? Those fields are going to go back into production. So the benefit is really in our production system, but at any given time, we're sequestering carbon in 1 3-year perennial cover crop. And then we do this other thing called bed flipping, where after, say, we grow like radishes or turnips or carrots or beets or some kind of crop that goes in, grows up, we harvest it. Once we've harvested it, the bed is done growing crops. What we do there is we sow cover crop and kind of flip that bed into cover crop within the growing season. So that's another example, like annual cover crop.
Okay.
We do a ton of that. We do a lot of composting too. So we apply compost to our fields as sort of an inoculant of bacteria and other beneficial microorganisms to the soil. It's those microorganisms that do the work of ingesting and digesting plant material and ultimately getting soil organic matter to increase. And soil organic matter is one way you can measure in the short term soil carbon.
As Caroline describes, there are soil management practices that can improve carbon sequestration, such as the practices of less intensive tillage or even zero tillage. This leads to less disruption of the soil aggregate structure. However, it should be noted that some scientists will argue that the benefits of increased carbon content in the soil surface horizons are offset by carbon loss deeper in the soil profile. This is according to climate-smart soils from Perspective Research. Switching from annual to perennial crops, like the Peas Farm has done for cover crops, typically increases below-ground inputs of carbon. Dr. Gay and I discussed the possibility of adding biochar to increase soil carbon stocks, which could also remove CO2 from the atmosphere. It decomposes slower than plant residue, and the carbon can be retained in the soil for several decades. Do typical agricultural practices, such as the ones in the Corn Belt of America, impact the effectiveness of the carbon cycle?
Well, they definitely impacted at like local to regional scales where, we talked about the land use in the U.S., a lot of it, or a large portion of it, is dedicated to row cropping agriculture in the Midwest states. So like a lot of that's corn ethanol.
Yeah.
Another big part of that is kind of the corn soy rotation. And so the corn soy rotation in theory is, there's some thought behind that where the soy is planted to bring in nitrogen. It's a nitrogen fixer to replenish nitrogen that's used up by the corn. So you can have more of kind of like a circular type economy. But we do know that it's net extractive, because in the Midwest often amendments are added like manure or other fertilizers to supplement those nutrient losses, because every year when you harvest the crops, like you're taking away those nutrients that have been quote unquote mined from the soil. And so when we talk about the carbon cycle, those plants are drawing down carbon, being locked in the biomass, but then we're using that for sometimes combustion for fuel with ethanol, or for consumption as food or feed for cattle. So those aren't net carbon sequestration systems. Those are net carbon sources. And so there is an impact. Like if we were to switch to, say, a perennial cropping system where we didn't annually have to harvest, and those plants stayed on the landscape, and perennials have deeper rooting structure, and you're building carbon deeper in the soil with the root turnover. Roots die on an annual basis. They become organic matter that microbes can access and turn over, like we just talked about. So those perennial cropping systems do a better job of, and it's still really hard to do anything as an extractive industry and have it be a net carbon sink or net kind of zero. But perennial systems would offer a much closer, I would say, like a net sink economy than the traditional row cropping agriculture that we're using now. And kind of the other alternative too we have to talk about is with when you're managing these systems, there are externalities, right, that aren't, if we're talking about the carbon cycle in terms of like the carbon that's used for tractors and farming equipment, if we move those to electricity, that would help offset some of that. Also, with the fertilizers that we add, when we add cow manure, we know that there's byproducts. I know you asked about the carbon cycle when we talk about, it's hard to not talk about climate when we talk about carbon. But when you add manure as a fertilizer source, we have off-gassing of greenhouse gases, nitrous oxide, methane, and other negative gases like ammonia that aren't necessarily a greenhouse gas, but you don't want ammonia in the atmosphere necessarily. So when you add those fertilizers, we have to think about this kind of trade-off of like, we're supplying the nutrients that the crops need, but we're also producing greenhouse gases that are going to contribute to future warming. So again, it's not carbon specific outside of the methane. We're talking about nitrous oxide as well.
Land use overall contributes about 25% of total global greenhouse gas emissions, and 10 to 14% is directly from agricultural production, mainly by greenhouse gas emissions via soil management. So, what's the cause of it? Are there any specific practices that actively increase carbon emissions?
There are lots. We even at the Peas Farm, use tractors, and we are growing at a scale where we need tractors. So we use fuel, we use plastic. Those are places where we're using fossil fuel. Where we're not is that we're growing our own fertility. We're also using biological sources of nitrogen, like manure. One place where we see commercial or industrial farms using or having a big carbon footprint is when they're with their use of nitrogen fertilizer. The production of nitrogen, chemical nitrogen fertilizer, has a big carbon footprint as an industry. So if you rely on that industry, then you're contributing to that ultimate emission from the production of chemical fertilizer. So we just use organic fertilizer. Other big sources of emissions, selling into markets that require processing. There's a ton of emissions associated with processing. And then the transport of crops from where they're grown to where they're processed, and where they're processed to where they're sold. So growing for a local market has a huge benefit, and growing food that people eat directly. Those things just get eaten or processed in people's homes, as opposed to processed into soybean oil or ethanol or goldfish or whatever it is. I mean, the energetics of farming, studying everything energetically and how much energy goes into the production of all kinds of materials that are used in farming it's really complex work. So understanding where our emissions are coming from is kind of complicated. We do what we can at Peas Farm to reduce our emissions from inputs that require lots of fossil fuels.
Have you seen any other changes in typical farming practice because of the concern about greenhouse gas emissions, or is there really a concern about them in the farming community?
Oh, there's definitely concern about them in the farming community. I think insofar as many people in the world are concerned about the anthropogenic causes of climate change. But I think like for most people in the world, it can be hard to make decisions around greenhouse gas emissions. What I've observed and what I've like research has shown that people make decisions because of their bottom line. Like if it makes more financial sense to stop using chemical fertilizer and transition to more local sources of manure-based fertilizer, if it makes sense to grow cover crops to grow your own fertility and, you know, maybe sequester low carbon that way, if it makes sense to like grow perennial grasses and support rangeland regeneration and sequester carbon that way, maybe people would be motivated to do that because of the benefit to the cows. But I find that people are motivated by the bottom line, by finances, because farming is a really financially tough industry. It's expensive to get into. The input costs are high. There's an element of biological uncertainty. You're at the whim of the weather. It's tough. So decisions that make financial sense first, but also that happen to have environmental benefits, that's probably what motivates people. Not to say that people aren't motivated by greenhouse gas emissions and stuff, but that stuff's pretty hard to visualize. But seeing like health in an animal or being able to sell into a market at a higher price point because you're growing organically or reducing your input costs and thus increasing your net profit because you're relying on outside inputs less. Those are motivating. And seeing the health of the land, you know, I think people know kind of what productivity looks like. Fortunately, a lot of these practices, these like organic or sustainable or regenerative practices, they can have a huge health benefits for plants and animals, but sometimes they take a while to transition to, and they sometimes require specialized equipment that can be expensive. So there can be some financial, cultural barriers to adopting them.
Because it's like they've done this one practice for so long, and then it's like, oh, you have to switch completely over, right?
Yeah, and like their equipment is adapted to like doing something one way, you know, so it's hard to change.
I think there's this stereotype that all farmers are simple-minded, conservative, and ignorant of climate change. I mean, I certainly thought that when I asked Caroline this question. But in reality, it can be hard to change practices when farmers experience success with old ones. Not to mention that some crops that are important to sustainable crop rotation may not have a big demand in the market or command high prices. As Caroline said, it comes down to the bottom line for farmers who can't implement more sustainable practices for their soil. With that being said, a key factor in improving soil health and carbon sequestration is intention and determination. Lifeline Produce, located in Victor, Montana, presents itself as an example for traditional Western farms to follow. They grow their own livestock forage and, as Caroline had described to me, produce their own biodiesel on site to power tractors and their farm delivery vehicles. They also have 25 kilowatts of solar panels. Lifeline Produce cites their growing practices to be cover cropping, crop rotation, and mob grazing. Caroline states that they're very intentional about decreasing their input costs and growing their own fertility. To me, and I'm sure to others, it would be ignorant to simply move on past traditional indigenous farming practices. The chief of staff for the Iowa tribe of Kansas and Nebraska, Missy Slater, explained the ideology behind agricultural practices as, looking at all of our decisions through a lens of life, and not just human life, we recognize the livelihood of water, of soil, of plants and animals. When life is at the core of your decision, sustainability comes naturally. Indigenous agricultural practices are incredibly different than industrial-scale agriculture. They're very localized and embedded in the ecosystem, climate, and community practices, so of course they vary by location. These practices are typically less extractive and better suited for long-term ecosystem health. A specific practice noted is the Three Sisters model, which is an intercropping method of planting corn, beans, and squash together. The beans contribute nitrogen to the soil, and the corn stalks serve as bean poles. Between the rows, farmers would cultivate a low-growing crop like squash or pumpkins. Its leaves would shade the ground, preserving moisture and preventing weed growth. Conducting the Three Sisters model is conducive to building soil carbon since it is traditionally a no-till practice. In the past, indigenous farmers saved the best seeds for the following season, leading to plants that were perfectly suited for their climates. However, a lot of this diversity was lost since indigenous nations were forced from their ancestral lands by European settlers. leading to European agricultural practices becoming mainstream.
Is there like really any way for farmers to quantify the amount of carbon and like other nutrients in the soil to see their progress, I guess?
Yeah, and like we're really good at doing that. We know how to do it. It's a tried and true. Like combustion analysis is tried and true, where you take a sample of soil from your field and you grind it up into a little small tin, and you combust at a really high temperature, and you can look at how much carbon is off-gassed from that. And so we can measure it very reliably, very accurately. However, the problem is that soils and soil carbon has high heterogeneity, meaning that if you were to go take a core in one location and take 2 steps to your left or right, there may be a drastically different soil carbon concentration. And so the problem with measuring changes in soil carbon at scale is this problem of measurement, because we can't go out, like if we're looking at the scale of, your backyard farm, we can go out there and take some soil cores and we can do a pretty good accurate analysis. If we're looking at like hundreds of thousands of acres in some of these cropping systems in the Midwest, the cost of that and the logistics of going out and taking that many cores is just not necessarily realistic.
Yeah.
And so the way around that right now is like building out models where we can, use math and soil sampling together to kind of create strong predictive models. If we know like, oh, this soil water concentration, this plant type, this soil type, if you induce this practice on it, we can build this model and we have a really strong relationship. And so we can just use like land use cover and pictures and known cropping systems and management techniques to model soil carbon gain or soil carbon loss. Is there validity in that? Yes. Is it as accurate as going out and measuring it with a soil core? No. But there's uncertainty in that, and so that's kind of the problem right now. And there's some new techniques being developed where we're using kind of like infrared spectra of kind of these like soil carbon scopes, where you can like use these quicker handheld devices to kind of get an almost instantaneous reading of soil carbon. Those are, I wouldn't say infancy, but they're still in research and development. Those would be a huge benefit, I think, to getting accurate field measurements in a short amount of time that you could then scale up. But yeah, measuring at scale is really where the issue lies with soil carbon right now.
Okay. Do you think that farmers could do that just by kind of like looking at their practices on like plant health and doing like, I guess, qualitative over quantitative kind of analysis to assume?
Yeah, like if we're not talking about carbon markets, you're just talking about like your backyard farmer, you can go out there and if your soil's the trajectory of your soil and the soil productivity, soil health, soil carbon, whatever term you want to use, by looking at the color, looking at the structure, right? It's going to be dark, it's going to be fluffy, you're going to have a rich smell to it. So like you can do that qualitatively for sure, and you'll see benefits in like your crop yield. You'll see crops with higher yield. They're going to be more nutrient dense. They're going to be darker in color. Yeah, I guess it just depends on the goal, but you for sure can take qualitative metrics and get a really good understanding of your soil's condition.
But in practice, at least locally, carbon sinkage isn't really that big of a concern. I asked Caroline about the extent of carbon sinkage's role in soil at the Peace Farm and whether it was a main focus for when they plant and harvest.
No. I mean, we're mostly thinking like in the short term, right? We're like, not only the short term, but we're thinking about, okay, how can we grow really healthy plants that are resilient to pests and can weather challenging, extreme heat or a lot of rain or whatever. And growing healthy plants is immediately very salient.
Yeah.
And in order to do that, you have to have really healthy soils. So having soils that have higher levels of organic matter is really important. And what's cool is that, organic matter gains in the short term do show, like, us wanting to have high organic matter in our soil means that we're going to do a lot of cover cropping, and we're going to try to like let as much crop residue as possible decompose in the soil. And in the short term, that benefits our plants and their health. And in the long term, if we can maintain those practices, we do see carbon sinkage.
Yeah.
But I think that we're more interested in the like short and near midterm benefits for production.
Yeah.
And for the health of the land. Of course, like soil carbon is just one thing too. Like we are also very interested in like creating biodiversity in all ways. Having patches on the farm that are undisturbed, patches on the farm that are full of native plants that have associations with native pollinators and native beneficial insects that keep some of our pest insect populations in check. And so we're interested in doing all of that. Well, if we grow more native plants and more perennial native plants, we're probably sequestering more carbon.
Yeah, exactly.
Like, there are so many things that we might be more motivated to do, like in the short term, that would have these long-term benefits too. We're not like ignoring those long-term benefits, but in the short term, more motivated to increase the biodiversity of the site and foster habitat for above ground insects and biodiverse soil microbiome.
Finally, we take a step back to the global scale and focus on soil and agriculture's effect on climate change in Part 3, Farm and Climate.
Ideally, I guess, what would be the best way to reduce emissions from soil and agriculture the quickest, but what is also stopping us from doing that?
Well, we talked about this a little bit before, but kind of these like large scale agricultural operations, they often are economically driven. And so kind of moving towards perhaps a system where we have focus kind of more on downsizing these large operations, where we can pair crop type, management type, soil type to optimize for reducing greenhouse gas emissions if we have to add amendments like fertilizers or manure. So doing it in a way that kind of can be more controlled, like I said, in terms of like applying at the right year, the right rate, the right type of fertilizer. Because like I mentioned, one of the biggest things right now is these externalities of soil and agricultural management, like greenhouse gas emissions from the tractors or the fertilizer addition. So if we can better optimize kind of practices based on region and soil type and kind of landscape level things as opposed to larger scale things, I think that's a good first step.
A solution that Caroline presents is that of restoring degraded lands to a perennial grassland that increases soil carbon storage.
Annual vegetable farms are really not where you can do a lot of permanent sequestration. From what I've read, the places where we could sequester the most soil carbon are on degraded rangelands. So pastures and rangeland that have been degraded, and then if you improve them, then you see a net increase in soil carbon. And then if you don't disturb them after that and you maintain them, that is actually like, that is more permanent. Degraded lands are opportunities, and then also pasture, because you have the potential to grow perennial grasses in perpetuity, as opposed to like a perennial cover crop for 3 years. And then you're going to put it back in production and grow all kinds of annual crops. So it's a kind of complex, field, I would say.
However, according to Climate Smart Soils, land use conversions may conflict with agricultural production and food security objectives.
All right, and then this is the last question, and it's very broad. Do you think that changing pretty much the industrial agricultural practices of like all the monocropping and everything you see in the Midwest and how we think of soil could provide the solution, or at least a solution to climate change?
Oh, for sure. I don't think there's one solution to climate change.
Yeah,
so I don't
think
it's
yeah, there's a lot.
But I do think it would require really big changes, not only in how we grow food, but in how we relate to land. And I do think it would cause a lot of economic changes in how we get food to people, and it would cause a lot of changes within people's eating habits and their cooking habits. And all of that is really tied to people's work habits and their family habits. If you work 3 jobs to make ends meet, it's really hard to have time to cook. Or if you have no childcare, it's really hard to have time to cook.
Yeah.
So, there's so many things that we need to have to change in order for, there to be wholesale adoption of, an alternative food system across the board, but it is inspiring to see the changes and gains that have been made. I mean, it would also require a huge redistribution of land, and we would need a lot more people to farm. And right now, not a lot of people are getting into agriculture, or those that want to aren't able to access land. They can't afford it, or they can't get a lease that's long-term enough to make it feasible. So a lot would have to change, but I do think it would be one solution, and it would definitely necessitate lots of other changes that I think might be really good for people too. But I'm not that powerful though.
It's not, I guess it's not super feasible, at least.
Well, is, I think, if you think about, I find that when I think about the big system, like, can I change everything in the Midwest? Oh my gosh, that's so good. But it's like, well, how do we make land more affordable in Montana? How do we make it easier to get into farming in Montana? How do we open up land for more young beginning farmers? Kind of put some boundaries around those questions and like think about your backyard or your community. I think it's a little bit more tenable. You know, how can we set up childcare systems so people have more time to cook? Or how can we create an economy where people have time to be with their family and loved ones and eat together? I feel like if we can put boundaries around it, it's a little bit easier, because they're hard questions to answer. But at the Peas Farm, you know, one of the most important lessons that I think students can learn is like what it feels like to grow your own food, harvest it, feed it to your community, cook with it, build a relationship with the land. My hope is that people do it when they're a student at the farm and they love it so much that they can't stop. And that they have to keep doing it. And so in that way, you know, they help promote this way of relating to food, way of relating to land.
Overall, changing how the West works regarding agriculture is difficult. Incentives for farmers would be needed, such as subsidies, regulation and taxation of fertilizers and tilling equipment, and supply chain initiatives that set performance standards for the contracted agricultural producers. It's truly a finance game, and farmers have to do what they can to help them meet the bottom line. Switching up long-standing practices isn't always ideal, but I think the main message is that it takes a lot of intention and care.